6.3 is a lesson on an integration technique called integration by parts, and it's a really handy technique. It's actually not included in the AP curriculum, but I always cover it because it's something that you'll cover in your first semester in college calculus. So that's why we're including it, and it's a really, really nice technique anyhow. But before we do that, I have several AP practice problems that I highly recommend that you try. So go ahead and pause, for each one of these so that you can work each one. And then at the end, I'll give you the answers for each one. So there's this one, and then that one. Move it every time. So number 3, 4, they're not numbered, but no, you'll want to number them because I'm going to number them at the end here. That's 4 and 5. Can you believe I do that every time? 6, there's 6 of them. Okay, so the answers were 1, 2, 3, 4, 5, 6. Okay, the first one was D, the second one is E, third one is A. I have a note that one was fun. I have a note this next one was tricky. C. And this one is A. That one is A. If you have any questions on those, ask during class. Now this is integration by parts. The integral of u dv is equal to uv minus the integral of v du. And I recommend saying that out loud a few times, having it be playing that through your mind, so if you just have, the sound of it, you'll help you remember it. The proof I'm going to skip just in the interest of time. I'm on my prep right now, so I have to get through all these notes before the bell rings. But I'll just say that the proof comes from the product rule. So you know how U substitution was like undoing the chain rule? Integration by parts is like by undoing the product rule. And I'm not actually going to do this, but I was just going to, so you know how the product rule is U times the derivative of V plus V times the derivative of U. And what you end up doing is you end up moving these around, integrating both sides and simplifying, and then you end up with this formula. Now, what we'll be doing is, so let's write this again. The integral of v du is equal to uv minus the integral, I memorized it wrong. I knew right away that this wasn't right, because, anyway. Let's come back. That's a u. The integral of u dv, it's important to write this correctly. It's been a year since I've used this, so my memory was rusty. The integral of u dv is equal to uv minus the integral of v du. If you say it over and over in your mind, you have a feel for what it sounds like, and then if you write it down wrong, hopefully it won't sound right to you, and you'll catch your mistake like I just did. So the goal is going to be, we're going to have an integral here that we're trying to integrate. And we're going to choose part of it. It's going to be a product of two things. And one of them is you're going to choose to be the u, and one of them you're going to choose to be the dv. And in order to choose your u, you're going to use lipit. And L is natural log. I is inverse trig. P is a polynomial. E is exponential. And T is trig. So if you have a natural log in there, that's you're going to want to make it your u. If you have both a polynomial and an exponential, you're going to choose the polynomial to be the u, because this is like an order of priority. So, like it says, in order. You're going to choose the trig at the very last. At the very least, you don't want it to be the u unless there's nothing else. So u is going to be something that simplifies when differentiated. So ln simplifies very nicely, 1 over x when you take the derivative of natural log. The inverse trig functions, I don't know that I would consider those simplified, but when you take the derivative of an inverse trig, you do get things in terms of x's. Anyway, let's move along and see how this works. So I'm going to write lipit down again to help us. So right here we have x. That's a polynomial. And then we've got cosine of x dx. That's a trig. So polynomial has first priority. So that's going to be our u. So we'll write u equals x. And then right away, we're going to take the derivative of u, kind of like we did with u substitution. Derivative of x is dx. And what I'm going to do here, I'm going to make kind of a little chart. I've got u, du. I'm going to have v and dv also. Let's also write down integration by parts again. It's the integral of u dv equals uv minus the integral of v du. Yeah, that sounds very nice. That means since this is my u, I've got the u taken care of, the rest of this thing has to be dv. So this whole thing here is dv. That way it matches this pattern right here. So dv, I'm going to just copy that down here in my little table. And then to get v, I'm going to integrate dv to get e. So the integral of cosine of x dx is sine of x. Now I have filled out my little mini chart. So now I'm going to come up here to the formula, and it's u times v. So u is x, v is sine of x, minus the integral of v, which is sine of x, du, which is dx. And then this is already integrated. We don't have to do anything with that. Just bring it along. And the integral of sine is negative cosine with a negative out front, so it becomes a positive cosine of x. And everyone said plus c. And that concludes our first example of using integration by parts. Find, example 3, find the area between y equals x e to the negative x. So I want to see what that looks like. We have been doing logarithmic regression in Algebra 2. Get rid of that. X e to the negative x. Close. Okay, that looks good. I'm going to do a zoom 6. Oh, we need to turn off a stat plot. Those we were using earlier this morning. Between 0 and 3, I'm going to change my window to go from 0 to 3. And I need to change my y to it so it's not so big. Oh, here, we'll do negative 1 to 2. All right. Find the area between that graph and the x-axis from 0 to 3. So we're finding this area right here. Okay. So everything's positive, so I can just set up an integral from 0 to 3. That's very nice. Of the function x e to the negative x dx. So it's all set up beautifully. I do notice I have a product. I've got a polynomial and I've got an exponential, so let's lip it. And I could see a song coming out of this one too. Polynomial before exponential. So the polynomial is going to be our choice for u, once again. Then we're automatically going to do du, which is dx. We're going to have v and dv over here. So this is my u. Oh, here, let's write the parts formula again. The integral of u dv is equal to uv minus the integral of v du. Say that over and over, get the feel for it. So dv is the other part of it. That's the e to the negative x dx. Now we have to integrate that in order to get e. So the integral of e to the kx is e to the kx divided by k. So in this case, divided by negative 1. And there we go. Now we can use the formula here and replace it. So u is x, v is negative e to the negative x, minus the integral of v, but it's negative, so I'm going to change that to a plus. Du is dx. And we get this. And this is something we can easily integrate. We just did it, in fact. This is going to be e to the k divided by k, and then plus c. But I am actually not right, am I? Because looking at this, actually, we're not going to add c. We're integrating from 0 to 3, so let's forget about that plus c after all. Get rid of u. Put a bar in there instead, going from 0 to 3. Okay, now plug 3 in. So negative 3 e to the negative 3 minus e to the negative 3 minus parenthesis 0, because the 0 here. But be careful here, this is not 0, this is minus e to the 0, which is 1. So we have negative, this is actually negative 4 e to the negative third, and that's going to be plus 1. Let's see if in my notes, I worked that out. If you get a decimal, that's 0.801. Which makes sense. It's a really thin area, so it should be a fairly small number. So this is out of our book. There's an exploration page, not too sure. Let's check and see. Oh, exploration 1 on page 325. All right. Consider the integral of natural log of x dx. Use integration by parts. Oh, and they even told us what to use. That's no fun. Don't look. Let's see if we can figure it out on our own. Lip it. Well, L, that's natural log. That's got to be my u. So this is my u, this is my dv. Let's again write the formula for parts. The integral of u dv equals uv minus the integral of v du. So I've got u, which is natural, here let's write this. U is natural log of x, so right away I take the derivative. That's 1 over x dx. Then over here I need v and dv. dv is going to be just dx. The integral of dx is x. So now we can use the formula u times v, natural log of x, times v, which is x, minus the integral of v du is 1 over x dx. So we're pretty much just plugging and chugging at that point. We'll bring down the x natural log of x, minus, this is just 1, the integral of 1 dx. X natural log of x, and then the integral, that's x. And we do have a plus c because we don't have limits. So guess what? That's the integral of natural log. That's pretty cool. It's not a formula we memorize because you could easily enough calculate it here. Integral of natural log of x dx. Oh, and in the exploration, they gave you the answer. So you're just doing the work and showing, yeah, that's correct. Now we're going to differentiate this to check it. So we're going to take the derivative. Okay, I'm seeing the product rule here, u and v. So u times the derivative of v plus v times the derivative of u. Minus derivative of x is 1, derivative of c is 0. This is 1 plus natural log of x minus 1, which is natural log of x. So we have success. Number 3, use a slope field of the differential equation dy dx equals natural log of x. Sadly, I cannot do that on my calculator here with the board. But you can try it on your own. Make a slope field. And then on that calculator program, you can enter a y, and you can put in this equation here that we found. And you should see that that equation flows through the slope field. And number 4, use the graph. So you can graph graph the y equals, and you can also graph the integral. And if you do that, you'll see that they are vertical translations of each other. So you can try that on your own and see if that works out for you. I highly recommend trying that. It's good to get practice with that slope field program and just seeing how the solution, the integral relates to the differential. Okay, here's another one. Let's lip it. So what we've got here is we've got a polynomial and we've got an exponential. So we've got these two. So once again, the polynomial, the x squared, is going to be our u. Our du automatically is 2x dx. Automatically, I'm going to have a v and a dv. Since this is my u, this is my dv right here. Yeah, dv. The integral of e to the x is e to the x, so that's my v. Let's again write the formula for parts. Integral of u dv equals uv minus the integral of v du. So I've got u times v minus the integral of v du. What do you think about that? Well, that 2 can come out. Notice again I've got another polynomial and another exponential, which means we have to do this again. We have to repeat the integration by parts on this integrand. What I am going to do, I'm going to bring along the x squared, or that's an e to the x rather. Let's change that into an e. Minus the 2 integral x e to the x dx. So right now, down here in a different color, go back to my trusty blue, let's just do the integral of x e to the x dx. In fact, I think we did that already, didn't we? And we could replace this integral with what it is. We'll just replace it up in here. I'm going to flip back through my notes and see if we already did that. Might as well use... Oh, maybe we didn't. Oh, I guess we didn't. It just seems so familiar. Oh, we did x e to the negative x. All right, never mind. We'll just do it again. Polynomial before exponential. So u is x, du is dx, dv is e to the x dx, v is e to the x. And it's going to be uv x e to the x minus the integral of v du. So x e to the x minus the integral, that's e to the x, and plus c, of course. So this part can go right there. And we'll go back to our raspberry color. X squared e to the x minus 2 parenthesis x e to the x minus e to the x. I'm just going to put my plus c on the very end. Okay, none of this is really going to be simplified, but if we want, we could distribute the 2. That's going to actually be a plus, right? E to the x plus c. All these terms are different, so we can't simplify anything. But we have accomplished our purpose and found the overall integral. We had to apply the integration by parts twice, but it did work. Now, as is typical, we normally do it the hard way, don't we? And then there's actually an easier way I'm going to show you in a little bit. But before I do that, I want to do this one kind of the hard way, because the hard way is actually the only way on this one. Well, maybe not actually. Well, let's see. Let's just do it the hard way, the long way that we've already been doing. Lip it. Let's lip it. This time we have an exponential and a trig. So the exponential is going to be the u. Du, e to the x dx. dv over here, v over here. So since this is u, this has to be dv. Integral of cosine x dx, sine of x. Let's put up the parts formula. Integral u dv equals uv minus the integral v du. See how we're doing this over and over and over? It's going to start getting stuck in your head, so you'll remember it. And, okay, so u is e to the x, v is sine of x, minus the integral of v du. Put that out in front there. Oh my goodness, look what we got. E to the x sine of x. Well, that looks a whole lot like this one, doesn't it? And in order to do this one, we had to integrate by parts, so I get a feeling we're going to have to do parts again. And I probably clued you into that a little bit because I said the long way. Bring that along. Or you know what we could do? Just not even write that, and just what I was going to do actually. Well, I was going to bring this aside and then put it back in. I think I'll do that. Let's go to new color. U, new color. U is, so again, exponential before trig, so exponential has to be our u. Our du is e to the x dx. Our dv is sine of x dx. And our v is the integral of sine, which is negative cosine of x. So, u v minus the integral of v, which is going to be negative, so plus, du, which is e to the x dx. And that whole thing is going in right here. So let me bring everything down, minus this whole thing. So I'm going to be negating this whole thing. So this is going to become a positive. This is going to become a negative. And you could probably get the sense that here we are back where we started. And if we keep going, we're just going to be completing this loop, this endless loop over and over and over again. And you'd be right, it's just going to go on and on and on forever, which is pointless, right? You might think. But actually, it isn't. Check this out. This whole integral is this whole side here is equal to the integral of e to the x cosine of x dx. So I can bring that down. And now, do you see something? We're trying to find the integral of e to the x cosine dx. Well, I've got that in here twice. What if I add this to both sides and get these together on one side and then solve for them? And we'll have it. So I'm going to add this over. I'm going to have two of these over here. Whoops, lost my x. Equals all of this. I could factor the a to the x out too if I wanted to. Doesn't really matter. I'll just leave it in there, I guess. And we do need a plus c. And now all we have to do, we're trying to find this integral, we could just divide both sides by 2. Cancel, and then here I'll just throw a 1/2 out front. You can put it across there. You could even do the whole thing because a c is a c is a c, so it's not really going to matter. But we did have to use the integration by parts technique twice to get it into a form that we could use to answer this question. Cool, huh? All right, after all that, now we're going to do it the easy way. This problem again, x squared e to the x dx. Remember we had to do it twice? Well, there is a shortcut. It's called tabular form. The funny thing is, every year I look at my notes so I remember how to do it. But if you don't do it enough, you're going to forget this method too. And for some reason, integration by parts just sticks with me better, so I can always remember it. U and its derivatives will go in this column. And dv, see how I am? dv and its integrals will go in this column. So just like always, we're going to use limit in the usual way. We've got a polynomial, we've got an exponential, so the polynomial is going to be the u. So the u is going to be x squared. That means that dv is going to be e to the x dx. then what you're going to do, just like these things say, we're going to take the derivative of u, so that's 2x. Take the derivative of it again, that's 2. Take the derivative again, you get to 0. You stop. Now we're going to integrate e to the x. Now fortunately that's very easy, so e to the x. Then you take the integral of that, that's still e to the x. I take the integral of that, it's still e to the x. Then we're going to stop there because we stopped there over there. Now, this is the thing. You're going to take the x squared and you're going to multiply it to the e to the x. Then you're going to multiply 2x times e to the x, and you're going to multiply 2 times e to the x. And there's going to be a sign. So this first one's going to be a positive, this one's going to be a negative, and that one's going to be a positive. So if you do that, you're going to have x squared e to the x minus 2x e to the x plus 2e to the x and a plus c. You can go back in your notes and see that this should have been the answer we got when we did this by hand. And I'll just let you go back through your notes and check that. But if you can remember this tabular form, you can see how fast it is for the ones that are repetitive. I don't know that I have tried it. I haven't tried that with the problem we just did with the cosine one. You could try that and see if it'll work. Because that one was a little different than this one. Is this our last slide? Almost. Try this one on your own with the tabular form. You can see, oh, you know what? I think this is actually, let me check. Is this similar to that one we did where we had the special, no. Well, let's just go ahead and do it. So u and derivatives, dv and integrals. Lipit. Trig is last, so it's going to be the dv. That means the x cubed is your u. Take the derivative, and differentiate, and differentiate. You could see this one, if you did it the long way, how many cycles would you have to go? 3 of them. It's x cubed. dv, that's sine of x. dx. Integrate that, you get negative cosine of x. Integrate that, you get negative sine of x. Integrate that, you get cosine of x. Integrate that, you get sine of x. We're back to where we started, aren't we? Now, start here, 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 plus, minus, multiply, and add c. So I'm going to have negative x cubed cosine x. We've got a negative negative, so plus 3x squared sine x. We've got a positive here, 6x cosine x, and we've got ourselves a negative there, 6 sine of x, and there's a plus c. Big long one. That would have taken a lot of trouble to do the long way. Tabular is actually kind of fun. Works right out real nice. Now this last one, I would like you to do this one on your own, please. So please pause and, oh, you know what? This actually, you don't actually need parts on this one, because I was going to say it's not a product. So do this one with techniques we've learned so far. I'll give you a hint. You might try use substitution. You might try rewriting it with a identity. But try it on your own, and then when you're done, I'm going to discuss this. Okay, now it's discussion time. There are actually 2 different ways to do this problem. One of them is to use substitution. And when you're doing substitution, you want your denominator to be the u, and you want it to be the inner function cosine of x. So the du, right away we take the derivative of cosine as negative sine of x. And then we rewrite it. Oh, that's dx. So we've got sine of x dx up here on top. That means that's the same as negative du on top. And on bottom we have u cubed. That's the same as negative integral u to the negative third du. Integrate that, you get negative u, add 1, that's negative 2, divide by negative 2. I know I'm going a little fast, aren't I? Plus c. So that becomes u to the cosine to the negative 2, so it's going to end up being down in the bottom. 1 over cosine squared of x with a 2 down there. Which, sorry for my clogging throat, which is the same as secant squared, so 1/2 secant squared of x plus c. That's one route you might have taken. If you didn't do it that way, you might have done it this other way. You might have used identities. You might have noticed that this is sine over cosine, which is tan, times secant squared, right? Because that's 1 over cosine squared. If you noticed it that way, this is pretty slick because the u, it could be tan, right? Because the derivative of tan is secant squared. So then you're going to have the integral of u du. That works very beautifully. That's u squared over 2 plus c. And then u is tan. So you get tan squared of x, 1/2 tan squared plus c. It appears that we have two different answers here. And is there an identity that relates these? Well, actually, there might just be one. There's a couple different ways you can rectify this. What you can do is try graphing both of these on your oh, we could do that. My calculator works. And I even have time, too, by the way. Let's check that out. Let's look at their graphs. So I'll do the first one. I'm going to write it as 1 divided by parenthesis 2 cosine x quantity squared close. Okay, just double checking my work. That looks good. And then the second one I'm going to write it, well, that's easy enough, 0.5 tan of x squared. And let's do a zoom 7 for a trig window. I like those. Oh, look at that. What do you think? Well, these two curves are vertical translations of each other, which is perfect because they vary by a c, which is a vertical shift. So it just goes to show you that both of these integrals are correct. It's kind of cool. Now there's another thing you could think about that I mentioned earlier. Is there an identity that relates these two? Well, there is one, and I don't have it memorized. I always derive it. It comes from the Pythagorean identity. And because I want to deal with tangent, tangent is sine over cosine, so I need to divide everything, since I want this to become tangent, I need to divide everything by cosine squared, which is beautiful because this happens to be secant squared here, right? So I've got 1 plus tan squared equals secant squared. So that means I could rewrite secant squared here. I could replace this with 1 plus tan squared. So I'm taking this formula and bringing it over here. I've got 1/2 times secant squared. Secant squared is the same as 1 plus tan squared. And then there's a plus c. So I can distribute my 1/2 plus 1/2 tan squared x plus c. And look at this, looks so cool. Here's my 1/2 tan squared. What's 1/2 plus c? It's another c. So this is the same as 1/2 tan squared of x plus c. These two equations are the same. The same because of the c, really. And that's a good way to end this lesson, with a fun thing like that.